This is a video on how to use a table as a representation of a function to both evaluate and solve. So let's talk about evaluating. So you're going to be given an input to find the output. Now remember, it's a function, or we're talking about functions right now, so that every input has exactly one output per function. So each function has a 1-to-1 ratio for the input to the output. Okay. Now we also have to consider the input versus output in terms of variables. So input, or the independent variable, versus the dependent variable. So it's a really good idea to look at the problem and to try to determine which of the variables is input and which is output. So on this first table of values, you can see that we have columns for years. It starts in 1900, goes to 2010, and a separate column just doubles. It's like a kind of a weird horizontal version. We could just really take all of this and plop it right down below the other one, and I think it would be more effective, but here it is. So we have these two variables, year and population. I am always looking for any unit of time as a likely independent variable. So for this problem, first we're going to say, our independent variable, or our input, is going to be the year, and our dependent variable is going to be the output, which is the population. So the question when it's saying evaluate is to say, okay, at what year what is the population in year whatever? So what is the population in 1940? Question mark. So we're going to look at the table. We're going to go to the year column. We're going to find 1940, and we're going to say that the population was 131. Now, I don't have any details around this, but I'm pretty sure this is the population of the United States, but this would be in millions. We don't have that information, so we're just going to have to say 131. So usually the table will be more descriptive. Again, we could do the same thing, change the year. What is the population in the year 2000? And the answer is 281. We could also turn around and work on it the other way. We could be given the output, and we could solve the equation. Okay? So if you're given the output, you can solve the equation. I could probably do a little bit better than that on the writing. So given a population, solve or find the year. Now you might have to estimate. So what if I said the population was 200, and your job was to find the year? So it's working backwards. We're given the output, and we have to find the input. So if I'm looking for a population of 200, no, 100, 150, 179 is close, 203. Ooh, it's really close to 1970, right? 203 here. So the population probably changed somewhere between 1960 and 1970 from under 200 to over 200. So I'm going to say just prior to 1970. Okay, if you want to speculate, you can, but we really can't tell. We don't know. Right? I can confidently say it happened before 1970 because 1970 had a population of 203. So we're working backwards. We're given the output, and we're going to work to get the input. Let's check out another scenario here. Again, we don't really have any specifics what these tables are for. We're just interpreting information from the tables. Okay, again, we're going to look for the input variable first. And again, like time is a very popular independent variable, the number of something is also a good input. Okay, and I'm just going to leave it as number of whatever, number of people, number of tomatoes, I don't know, anything. Okay, so the input is the number, and the output is the cost. So let's find the cost for 4 people. And then we're going to go to our table, number of people 4, and the cost 250. How about finding the cost for 9 people? 4, 6, 8, 10. 9 people is somewhere in between. Now, we don't know for sure, but if we had to guess what's going to happen between 8 people and 10 people, it looks like for every 2 people, it's going up $100 pretty consistently. Right? So if it's going up 100 per 2 people, I can make the guess that it's going to go up $50 to an even 500 for 9 people. So we can use some logical reasoning to get that number. Let's do one other type of problem here. Here we have 2 separate tables that seem to be connected, right? We have one for math, and we have one for language arts. So it's a number of questions and estimated time. Okay, 25 questions, 87 minutes. 20 questions, 88 minutes. 30, 102, 35, 148. So it looks like there's just varying number of questions in each, varying number of minutes in each. So maybe we want to keep track of math and language arts. Maybe the questions are going to be specific to one or the other. Question that could be asked is, how much more time... Oh, we can't do that. Sorry. Let's do find math time for 40 questions. And I would call the number of questions, right? Number being a good indicator of independent variable. Okay. So again, we're looking at the math section. We're looking at about 40 questions, which is somewhere in here. So we have to estimate. It's probably going to be closer to the 147 because 40 is closer to 45 than 30. So we're looking at somewhere in the 120, 130 range. Okay, again, it's an estimate. Any number between 102 and 147 is acceptable within reason. Okay, it probably should be, if you cut that in half, or you found the median of those 2 numbers, that's going to be 249. So 124, 125 is about halfway. You want to be on the closer side of the higher number because the halfway point, okay, it's clearly the 40 is closer to the 45. So 130. Okay, find an approximation for how long or how many questions on an English exam, language arts, oh boy, no room. Didn't think that through very well, did I? How long or how many questions on an English exam that took 100 minutes? Again, we're estimating. So we go to the correct place, language arts, ELA, right? We go to the estimated time. 100 minutes is pretty close to 88. I'm going to say like 25, 23 questions. So there's some instances where it's really specific and you have to know that, oh, they match up perfectly. There's others where you have to find the value in between other values.